Hello and welcome. In this video, we're going to take a look at another form of rationalizing, and that's where we have roots, but we have some other forms of addition or subtraction in there as well, combined with that. This is going to be especially important when we want to take an expression involving roots with addition and subtraction in the numerator or denominator, and try to simplify it somehow to maybe make it into a more meaningful format. Now, it's best to start off with where this theory comes from, and we can take a look at one of our special product formulas. So we know the difference of squares formula here, a plus b times a minus b, is a squared minus b squared. Now consider for a moment what happens if a is something like the square root of a value, square root of c for instance. And if we apply that same difference of squares formula, we get the root of c times the root of c, but root c squared is simply just c. But we still end up with the difference of squares. The change here is that the square of a square root is simply just what is inside the root. Similarly, what if b is a root? And we have a plus root c, and we have a minus root c multiplied together. Still looking at difference of squares, we get a squared minus root c squared. But root c squared is just going to be c. And we can go even one further. What if they're both roots? What if we have root c plus root d times root c minus root d? All right, difference of squares again. Root c times root c will just be c. So that's like our a squared. And then our b squared in this case is root d times root d, which is just d. So we get c minus d. All right, so they kind of they almost look like they break the rule of difference of squares because it doesn't really look like a square minus a square on the right hand side, but in fact it is. It's the square of a square root, so this still works. And you notice that inside these parentheses we have roots, but when we multiply them on the right hand side, there's no more radicals, there's no more roots there. And these two factors, they come in pairs. These are called conjugates. And really a conjugate is just when you take some expression involving two terms with a root in either term and you change the addition to a subtraction or vice versa. That means that when you multiply the two conjugates together, you end up with an expression with zero roots in it. And that can be used in one of two ways, rationalizing the denominator or rationalizing the numerator of some sort of fractional expression. So here's a quick example. All right, here's an example where I have a root in the bottom, but it's 2 minus a root. That means I have two terms down there. Now, what if I wanted to get rid of that root from the denominator? Maybe I can simplify things a little bit better if I put a root in the numerator, but get rid of a root in the denominator. Well, by properties of equivalent fractions, I have to just take a non-zero factor and multiply top and bottom. And I know that if I multiply by a conjugate, in this case 2 plus root x, then when I go and distribute out the denominator, making sure I've got brackets appropriately here, I won't have any roots in the denominator. Instead, I'll have a new factor on the top that has 2 plus root x. And so as a result, this ends up being a 5x times 2 plus root x, and that actually makes the numerator maybe a little bit worse than it initially was. But in the denominator, 2 times 2 will be giving me the 2 squared part, and the root x and the root x, when you multiply those together, will get us x. So it's 4 minus x. And remembering difference of squares, when you multiply a plus b times a minus b, the middle terms cancel out in FOIL, so this is all that you're left with. Now this is called rationalizing the denominator. Now, there's also the possibility that we have roots in the numerator of an expression, and it may be easier to simplify if we have our roots in the denominator. Let's just take a look at that. And here's an example of an expression that we'll see in a calculus course, for instance. And in this case, we have a root on the top, and it's got a negative sign. So if we want to rationalize, we're going to have to find the proper conjugate. In this case, change that negative sign to a plus sign. But the radicand is not going to change signs. 9 plus h is still going to have to remain 9 plus h, so that when they multiply together, the root times the root cancel each other out, and you end up with no more roots in the numerator. Make sure that you've just changed the single sign from a -3 to a +3. And then, of course, to make this an equivalent fraction, we're going to have to multiply top and bottom by the same non-zero factor. Now, you can actually take a look, and this is essentially just the same as this top form here. Root c plus b times root c minus b equals c. In this case, that would just be 9 plus h. Minus b squared. Okay, so that would be, in this case, minus 9. And on the bottom, we have h times root 9 plus h plus 3. And what's the point of rationalizing the numerator? Well, in this case, we went in kind of blindly and tried it out, but then, as a result, a 9 and a -9 are going to cancel out, and that leaves you with just h in the numerator. Now that we just have an h in the numerator, you can see that that actually has this common factor with h and h in the denominator, leaving us with just 1 in the numerator. And it ends up becoming a much more simple expression than what we started with. And that would be the main purpose of rationalizing the numerator, is hoping to come up with an expression that is a little bit more simplified. Now, of course, just like I said, we went in blindly there and tried rationalizing the numerator. It's just a strategy that you might try to apply whenever you see some sort of form of root a plus or minus root b, or one of the two terms has a root in there. And if you give it a try, you can see whether or not something's going to simplify. And we'll see that if you're going into calculus, this kind of expression comes up a few times with sort of the expectation that it will simplify. So then it becomes a pretty common method to try to use. Anyway, that's it for this video, and I guess I'll see you in the next one. Thanks for watching.